Okay, good morning, everyone. I hope you're doing well, and I hope everything went well as far as the online homework. Just taking a look at the grade book, it looks like you guys are largely doing okay with that. In the future, if you haven't had to use it yet, if you do run into troubles, I'll remind you that in the syllabus, there's a table that shows when some of us are available, either myself, the other lecturer instructor, Ben, and two assisting graduate students who are essentially waiting in Zoom to help you out if you ever need it. So the times are listed up there and the Zoom contact information. They're there a good chunk of the day on Mondays, Wednesdays, and Fridays, and then in the afternoon for the most part on Tuesdays and Thursdays. So you can find them if you need. You're also welcome to email me if you have any questions, and I can try to get back to you as soon as I can. And when you go to the Zoom hours, you can bring any questions you have, whether it's on the written homework, online homework, the labs, and so on. And while I'm talking about that, let me also remind you that there is a written homework and a lab both due by Monday morning, like Monday by 7:59 a.m., right before this session starts. Now, with that, I want to open up with any questions that you guys have, either from the recent online homeworks or just anything else you've seen in the videos so far or that we talked about on Monday. So if you have anything, feel free to ask it in chat and we'll go over those before we get into the uh, new material for the day. All right, I've got a question to look at. Question 4 from daily homework 2. So let me bring that up and we can look at it. If I remember right, that's one of the slope field problems. Yeah, and in general, just so you're aware, I'll set aside the start of each of these sessions for questions, just so you have time to get questions answered live. Let's bring up this here. All right, if we're looking at question 4 from the second online homework, essentially we have a solution, but we don't have the slope field. In some of the other problems and the video, you would have a slope field, but not a solution. Now, if you have the solution already, that's pretty nice. You can approach this one of two ways. So let's say we have this one. This is what I was given randomly. So say you have a solution of y equals e to the x cubed, for instance. Now, if you want to know what the slope field looks like, you could do one of two things. You could either look at a given slope field. Say, for instance, you're given something like this for your slope field. This is just a kind of rough example. You could find the graph of this function and then see if it matches up with the slope field. So for instance, this function roughly is going to be like e to the x, but a little more extreme because it's x cubed. But let's say I color this orange. How I know that that's going to look is very roughly like this. So that x cubed is going to keep whatever x is, keep its sign. So if x starts positive, it'll stay positive. If it starts negative, it'll be more negative. So it's going to look something like so. There may even be, let's see, a little bit of a dip. kind of like this. And if we look at this slope field over here, for instance, we'll notice that that doesn't really fit this solution. Like if you graph this solution through here, that there's going to be a part, namely over here, where you should have positive slopes, but you have instead negative. So you could just graph the solution through here, or you could alternatively, if you wanted, you could just take the derivative of the solution function and see if the slope field you get from taking the derivative matches what you have here. So if you take the derivative of this e to the x cubed, you'll get, let's say, we'll put that in another color. Say you get dy dx, taking the derivative of this, you'll get, I think by the chain rule, 3x squared e to the x cubed, or e to the x cubed. And now if you graph that, for instance, take the point where x is, I don't know, let's say 1 and y is equal to 0. And if x is equal to 1, here you'll get something positive, but here you'll get something that that's 0. So you can tell by this method that this doesn't match this slope field. So there's various ways you can do it, either using the solution, graph the solution through, see that it doesn't fit, or just take the derivative, get the slope field, or get the equation and see that the slope field from that equation does not match up with what you have here. So that's the general idea for that problem. Now there's a few questions, so let me address those. First, let me do a quick check. Can everyone see the screen okay? Just let me know if you can or not in the chat. Okay, good, good. Yeah, maybe I had it off to the side of my computer. So yeah, if the screen doesn't seem to be appearing on your screen fully, just let me know and I'll adjust it. But let's see. Another question someone asked. Okay, so this is how you would get how you would match up a slope field to a solution or to the slope field itself. But let's say you had the slope field to begin with and you wanted to match it to an equation, for instance. So let's look at another page. So say you had a slope field. And let me put these in, maybe I'll do cyan here. And let's say it looks like okay, so here's a slope field that I've just drawn kind of quickly. I mean, for in any given horizontal line, these slopes should all be the same, but I'm drawing it by hand, so it's going to be a little off. And let's say you have all these different, let me think here, different slope fields, such as dy dx. Maybe one is equal to cosine of x. Maybe one is equal to, let's say, x plus y. One is equal to y squared. And then one is equal to, how about y minus 1. Okay, so here are some example first order differential equations. And over here is the slope field. If we want to try to decide which one of these differential equations matches to this slope field, then what we'll do is check the nullclines and isoclines. That's the best way I find to do it. So for instance, and actually there's also another way you can quickly sort these out or try to eliminate some possibilities using what we'll talk about today, which is deciding whether an equation is autonomous or not. So so for an autonomous equation, which we'll get to the definition in a bit, it only depends on the dependent variable. So the independent variable, in a sense, is not present. It doesn't change the differential equation. For example, if you write each of these in prime notation, you have y prime is cosine of x, you have y prime is x plus y, you have y prime is y squared, and then y prime is equal to y minus 1. In the first two cases, we can see that as you change x, your differential equation changes. Importantly, your slope changes. That means that as you move over to the right, your slope should change. But we see in this case how I mean for it to be drawn. I couldn't draw it perfect because it's by hand. But the idea is if we look at a given, let's say, y value, say here, and then we move over to the right or left, the slopes don't change, they stay 0. And that should be true everywhere. The slopes here, all in this horizontal line, are the same. That means as long as you keep y the same, but you change x, your slopes over here are always the same. But that should not happen in these cases. The reason being is that it involves x here. So as you change your x, your slope should change. But that doesn't happen over here. So right away, you can see that these two cannot match this slope field. That is this one and this one, because they both change the slopes as you change x. So you can rule these out immediately. For the next two, also what we'll talk about today is essentially evolving equilibria, which is, as you know it from before, is looking at nullclines. One student's reporting that they can't hear me. Quick check, can you guys hear me? Okay, thank you for reporting in, appreciate it. So what we'll look at here is nullclines, and we'll study more of this today with looking at equilibria. But the idea is finding out where are these 0? That is, where is this 0, where is this 0? In the first case, this is only 0 when y is equal to 0. So that means there should be 0 slopes only when we're looking at this line here. Since there's also 0 slopes here at some positive y value I haven't specified exactly, that means it can't be this one. So that rules out this equation. Mostly you want to do this by elimination, just eliminating the ones that can't be, because it'll often be really hard to nail down exactly which it could be, because if your graph is not labeled, for instance, this could be the value too, and you don't want to right away necessarily say, oh, it's going to be this one, when this could be the wrong height. So what I would do is just rule out the ones to begin with. It's definitely not. And then if you have a few that are similar, you can investigate further. I'm going to scroll back up through the chat, see if there are other questions. Okay, there is another question. I think it's a pretty good one. So let's look at that. And that's essentially for the inverse function theorem. we won't go through a whole problem, but we'll just get the idea of what it looks like. So let's say you have something like dy dx is equal to y cubed, and you have y of 3 is equal to, let's say y of 4 is equal to 2. So what that's essentially saying is, if you look in the xy plane, the solution to this differential equation here is going to pass through this point here. And maybe I'll color that point. Let's just do red. Let me now put that point in the plane. So let's see, x is about 4 and y is 2. So let's say we have this here. And now the solution to this differential equation here should pass through this point. And when it's at that point, it should be something positive. So it's going to kind of go like so. I'm not going to draw the rest of it because I don't know exactly, but the point is it goes through this point 4, 2. And if we just kind of track that geometrically, we've got 4 for the x value, 2 for the y value. Now, if you do some switching of this differential equation, that is, you effectively switch the independent and dependent variable, what you'll get from that is, let's see, dx dy is equal to 1 over y to the third. And now if you want a new point, your point doesn't really change. You still have x is 4 when y is 2. So you're looking at the point x, y, where this is 4 and this is 2. And then you're going to switch these, and now you want the point yx, so you just swap, and then you get y, or x of 2 is equal to 4. So since you're changing the independent variable and the dependent, you just swap the 2 and the 4, because before this was independent, this was dependent, and now we're changing that, so it's independent and then dependent. So we tend to think of it as in the order of independent and then dependent. Okay, so these were some questions we've looked at. Now let's go ahead and jump into the material. I'll jump back to the first page just to see an outline of what we're talking about today. So we'll start with the definition of an autonomous equation, which I've alluded to here, if not basically told you outright. We'll look at some slope fields of autonomous equations, which I've also mentioned, and I think will not be too surprising to you. Look at some examples, and then when we're working with autonomous equations, we're able to draw something called a phase diagram. A phase diagram is effectively like a compressed slope field, where it gives all the information of a slope field for an autonomous equation, but it just does it in a simpler form, so to speak. And you'll see why I call it compressed when we look at it. And then we'll look at some logistic and really population growth type equations, talk about those a little bit. You'll later have a lab. I can't remember offhand when it is. I don't think it's maybe for a few weeks, but you'll investigate that behavior further, but we'll at least introduce the idea so it's not so foreign once you encounter it. So first, let's just look at the definition so we have it formally. So an autonomous equation is one, as I've mentioned, it doesn't depend on the independent variable. So we're defining an autonomous equation. I'll put that in this blue. And I'll highlight does not. So that's the important thing here. Just some really quick examples of this. We've seen a few, but just so that we're really focused on them now, would be something like dy dx is equal to y, which in order to really convince yourself that it's autonomous according to this, what I'll sometimes do, if it's not immediately obvious to me, is just rewrite in prime notation. And if you do that, because the prime doesn't have the dx, for instance, now you won't see the independent variable. So this is what it's meant by does not depend on the independent variable, that you don't see it in this prime notation. Yes, you're taking derivatives with respect to the independent variable, but changing the independent variable, changing the value, does not change the actual differential equation, which is what we see here. Some other examples might be something like this. It could be something that is not linear or not nice. You know, it has cosine of some derivatives, which we're definitely not going to grapple with. That's a little beyond us. I'm not even sure actually offhand if these are solvable when you start doing things like this. But other examples might include something like the following. Something like this, where we have the 10th order derivative, the 6th order derivative. So take the derivative 10 times, take the derivative 6 times, and cosine of 3 here, notice that's just some number. Now, we want to specifically look at autonomous equations and think about their slope fields. So let's look at the concept of that. Now, if you have a differential equation, dy dx, and it only depends on the independent or on the dependent variable, that means it's equal to some function, let's say f, that only depends on y. Now, like we actually looked at in the earlier questions, if you graph the slope field, let's say I've got axes here. Whatever your slope is, which I'm going to do just a sample slope, here is just some f. I haven't specified it, so we can't get exact slopes. But if you think about getting a slope, let's say like so, at this point, as you change your x value, but keep y fixed, that is, say you have, this is the point, I don't know, y, call it y naught maybe. Why not call it y naught? Then we have that value is f of y naught as far as the slope. So the slope is given by f of y naught. Now, if you change the x value, so you're no longer at this point 0 y naught, but let's say you go over here and you keep the same y value, keep the same height. You substitute the point xy into the function f. Well, it only takes the input of y, so it's not going to change that value. Therefore, you're also going to have the same slope there. Or, you know, again, I'm drawing it by hand, so I'll try to get the same slope, something like that. Yeah, there we go. And so on and so forth. So as you change the x value, but keep y value fixed, your slopes won't change. I'll try to, actually, I can copy paste this. That'll keep their slopes the same. So as you move over, keep the same height, your slopes are all the same. And let's say to fill this out a little more, we have a zero slope here. And let's say we have something like this, and so on. The big feature is that as you change your x value but keep your y value fixed, the slopes don't change. Now, how that ties into compressing the slope field, like I said, it's essentially, if you think about it, the x value no longer gives you any information. As you change it, the slopes don't change. So when you look at, let's say, this line here, the horizontal line, and look at all the slopes there, the slopes are always the same. So it doesn't matter what x is. So x is in some sense redundant. All you really need to know is at that given height, what is the slope? So it's kind of like all of this here is just unnecessary. You don't lose anything. You could recreate the slope field just given this partial single axis, because the slopes there will tell you the slopes everywhere along the real axis. Now, I'm going to do a screen switch. There's an applet that grass slope fields that they're pretty nice. I think I showed it in one of the videos. So I'm going to stop share of the iPad, and then we're going to go and share, or try to share this here. Okay, quick check-in like usual. Can you guys see the slope field, like a slope field in a tab? Okay, good. Thank you to those who checked in. Now let's say, looking at this slope field, it's cosine x plus sine y. I'll try to enlarge this to make it a little easier to see. So it's cosine x sine y, and you can see if you look at a given height, let's say we just travel along, actually let's just do the x-axis, makes it easier to keep track of. If you look along the x-axis here, the slopes change. They go from negative in this area to positive in this area, and so on. And that makes sense because you're changing x in the differential equation. So your slopes change. Now let's say we get rid of cosine x and we just have sine y. We update it. And now you see that indeed they're in line here. All along the x-axis, they're the same slope, happens to be 0. Up here, they're all the same slope, and so on. And as was pointed out in the video, notice these have arrowheads, and you can draw the arrowheads or not. It doesn't really matter. When we're working with slope fields, we're always drawing arrows to the right or thinking of the slopes as going to the right, so it's sort of redundant. But if you do a few more, just to give you some examples, let's say we do y squared, looks like this. If we do e to the y, looks like so. Maybe I'll try, what would be another one that we haven't seen? 1 divided by y squared plus 1, or y squared plus 1, something like that. So here you can see it's really striking that for these autonomous differential equations, their slope fields are very regular in this sense, or in the colloquial sense, that you really only need one line to capture all the information you need. And then it's just kind of copying and pasting that one vertical line of slopes over and over and over again. All right, I'm going to jump back to the iPad screen. And for your reference, I got that slope field app from this site here. In the Bennett textbook that's linked in the syllabus, I think it's Geometric Interpretation, maybe one of the early links. You can find that app if you're kind of ever curious to play around with it, or you feel like it might help you out on one of your homework assignments or what have you. It's a nice app. Okay, so now let's next look at slope fields of autonomous equations. Actually, essentially we just did that, so that was with the other screen share. I've alluded to what phase diagrams are, so let's go ahead and look at that more formally. So if you've got a differential equation of the form dy dx is f of y, and you want to, actually, let's just do a specific, no, let's do it generally first. So if you've got dy dx is f of y, and you want to compute the phase diagram or graph that, what you're essentially doing is a partial slope field in some sense. So how this looks, the phase diagram is, in a sense, a compact slope field. And what you're doing is you are just taking a single axis, a vertical axis, which you can think of as the axis representing the dependent variable. Let's say I graph that here. And you're just marking whether the slopes are positive or negative, and that's it. So if this is the y-axis, we mark whether slopes are positive, negative, or zero. Now notice in doing that, you aren't even worried about how positive they are or how negative, whether it's a very shallow slope, something like this, or whether it's a very steep slope, something like this. You're only tracking whether it's positive or not. And the way to do this is to actually start with the zero slopes. If you start with the zero slopes, then you can divide your interval up into, or you divide your axis into intervals, and then you just check anywhere in those given intervals. And as long as you're working with a nice continuous function that's continuous over the whole y-axis, that's all you need to worry about. I see a question about undefined slopes, and we can talk about that in 1 second. That's a good question to consider. So let's just suppose for a moment that we have a differential equation where this f function is continuous over the whole real axis. For instance, say we have dy dx is equal to, let me think, how about y squared plus 3y, or not y squared, yeah, y squared, plus 3y plus 2. If this is our differential equation and we want to know where this is zero, that is, where is the slope zero, where is this function zero? Well, thinking for a second, just in terms of algebra, we can factor this part. And if we factor it, we'll get y plus 2 times y plus 1. And now there are two places where this is equal to 0. This is equal to 0 when y is equal to -2 and -1. So now if we graph those slopes or those points, well, let's say put here is y is equal to -1. Here is y is equal to -2. Now we essentially have three intervals. We have the interval where above this, is one interval, so all y greater than -1. We've got y between here, -1 and -2. And then we have all the y that are strictly less than -2. So we take these and we do test points in here. Suddenly, I apologize for my long pauses. I'm getting deja vu. I feel like we've done this. Was this in that slope field video? For those who watched it? Why do I feel like I've said this before? Like recently? Okay. All right. So yeah, thank you for those who are confirming that you haven't seen it. Good. Or that it wasn't in that video. Yeah, I don't know why I thought maybe I had put it there, but then cut it out. Okay. So what we're going to do in each one of these intervals is do a test point. Now, the function is nice such that and we'll look at more of this in a second, but the function is nice such that once you have the zeros, between those zeros, you're either strictly positive or strictly negative. And someone asked a question earlier, which was good, about what happens if you have undefined slopes. And there you have to be a little bit more careful. But if you're working with a nice continuous function, continuous over the whole y-axis, then you can do this. So we found the zeros, and now we just check a test point inside each interval. With, let's say, the middle interval, let's do yellow. We'll do a test point. So we'll test, or maybe a test value, y equal to, it's got to be between -1 and -2. So how about y equals -3/2? Now, if you substitute y equals -3/2 into this equation, you'll have, let's see, -3/2 plus 2. That's going to be positive. -3/2 plus 1. That's negative. So you get a negative times a positive. So overall, you get a negative number. You actually don't care what the value is. You just care, are you positive or negative? That's it. So the test value, and maybe I'll move some of this over just to give some space here. The test value is -3/2. We could have used a test value of like -5/4, -1.223 or what have you, just as long as it's between -1 and 2. And what we get is that the slope is less than 0. Now, to indicate that, what we'll do is then draw a little arrow going downwards. That means we're decreasing. If we had slope field, what would happen is we'd have some negative slopes. They might look like that. So if we kind of expanded this out, and the slope field, the slope lines here are not part of the phase diagram, but just to give you an idea, you might have just negative slopes in here. They're different magnitudes of negative, almost definitely, but they're negative. That's all we need to track. And then likewise, if we do a test value in the other intervals, let's say do a test value y is equal to 0. If you substitute 0 into here, you get 2 times 1, and that's positive. And again, you only care, are you positive? Oh, well, those are tied together now. You only care, is it positive or not? Same thing if you go down to the bottom interval, do a test value, y is equal to, let's say, -3. And again, we could have used y equals -1,000,000 or whatever, so long as it's in that interval. I just chose -3 because it was the closest integer. And if you do that, -3 will give a negative times negative, so you get positive. So now we put an arrow going up and then an arrow also going up here. And someone asks, are these phase diagrams better representation than slope fields? For autonomous differential equations, they are, I wouldn't say better, but in some ways they're nicer. They're nicer because they're more compact, so you can very quickly see what's going on with less presented information, if you will. So there's less to kind of sort through. You can just quickly see, okay, as long as we have a y value in this range, we know we're going to be decreasing and so on. The slopes are going to be 0 here and what have you. So it's just a little bit cleaner in that regard. But in fact, it gives you most of the information. You get a little bit more by having the whole slope field, in the sense that you can see what the solutions do. But once you're comfortable with phase diagrams and you've done enough of these, you can basically see that just from the phase diagram. Like I can tell you right now what the solutions are going to look like here, and I'm sure you'll be able to do that relatively soon as well, if not already. And another question is, well, can we or would we apply this to non-autonomous differential equations? And the answer is definitely no, because you would need to have another axis for that. Notice we essentially just have one axis, y. If we had x in this function, this f of y, if it was f of xy, we would need another axis because this function, the values would change as you changed x. So this will only happen when you have functions that are just dependent on the dependent variable. Now, you have some interesting possibilities here, or it's sort of interesting to consider the places where the slope is 0. And actually, let's take this exact thing and let's expand it out a bit. So here's the phase diagram. And we're essentially doing an example. So I'm going to move some of this work to the example area, if you will. So just to be clear, this thing is the phase diagram here. If you wanted to compare it to the slope field, we would then essentially expand this out. So think of it like, moving everything out to the right. And then we'll talk about these points here that I started to mention. So let's now kind of expand it out where we recover the x-axis, so to speak. Now I guess up here would be 0. And now here you've got the points y. I'll try to draw it roughly in line. Y equals -1, y equals -2. And now if you think about it, the null lines, going back to a term we saw in the video, are where this is equal to 0, where the slope is 0. Here, those were the 0 values, or the values that gave us 0. And if we graph this in terms of slopes, what we'll get are 0 slopes. So I'm trying to draw these as horizontal as I can while doing it quickly. And I'll just say now that I've done enough of these, I can fill in the slope field. So let me do that. And actually, let me distinguish between increasing, which we'll call, how about blue? Or maybe cyan. Okay, I'll just redo this. And then we'll let decreasing be the yellow here, just so we can distinguish a little more easily. That I've done enough of these, and again, if it's not already apparent to you after you do a few of these, I think it'll be obvious to you as well. that essentially it's going to look like this. As you get away from these zero slope lines here, your values are going to initially be something like this. So just slightly positive. And I'm trying to draw them again so that they look like they all have the same slope. Then they're going to be a little more extreme here. And we'll look at, as I mentioned, a way to see that this is true. Oops, actually, all these slopes should be yellow because they're negative. Okay, so something like this. Now we'll be able to see why this is true, or you'll be able to see why this is true, why I would have drawn these slopes where, for instance, in this line, they're more negative than this one. Hopefully that'll become clear when we look at another concept or extend this concept more. But for now, what I want to highlight is this fact that we have zero slopes at these points. Now, if you graph solutions through here, I'll put the solutions, let's say, well, orange, actually green. We're not using green. Let's do that. If you graph solutions through here, for instance, and actually I want to preserve this just in case I want to undo some things. So I'm going to move that to the next page and then jump right back. So this is just a deposit there. Now, if you start on this line here where y is equal to -1, the slopes are going to be 0. So that means that there's going to be no change. If your slope is always 0, you're just moving to the right horizontally. You never increase and you never decrease. So if you start there, you're going to stay there. So it's going to look like this. So that would be one solution through here. The same thing with this. These are both solution lines. Now, the reason that is because if you have, let's say, y is equal to -1, substituting y equals -1 into the right-hand side here, just by definition, that will give you 0. If you take the derivative of a constant function, y equals -1, you'll also get 0. So your left-hand side and your right-hand side are the same. So this constant function, or as we've seen it earlier, this singular solution is a solution. And there's actually two of them. There's the one here, and then there's the one here. Now, just because we have a second degree polynomial here doesn't mean there's always going to be two lines. There could be one or none. But in this case, we happen to have two. Now, these are called not only singular solutions in the general sense, but also equilibria or equilibrium solutions. So there's two equilibrium solutions. So notice that they're also singular solutions, but they, in this case, we call them equilibrium solutions because they will tie into the broader context of working with these things. So let me jump to the chat, make sure I'm getting everyone's questions. Someone asks, can we use phase diagrams or slope fields? The answer is definitely yes, you can, either one. If you want to show what the solutions look like, then you would use the slope field. So that's for showing the solutions. Notice it's just too compact in the phase diagram that we won't be able to graph the solutions because we need the x-axis to show how it changes as x changes. But if you just want to capture the essential information, the phase diagram is good. And the slope field essentially gives you even more than you always need. You don't always need what the slope field gives you. So we have two equilibrium solutions. There are other solutions though. Let's try a purple and see if it's distinguished enough from the rest. Yeah, I think that'll do. What I'm going to draw here are now called typical solutions. So these are just some sample solutions. Notice if you start out, let's say here, what's going to happen is the slope is negative. So it's going to push you down. It's going to push you down like this. And then it's going to start to push you down more as you get closer and closer to more negative slopes. And then you're going to start to be pushed down less. So you're going to get something like this. So if we're kind of following the slopes, it does a little bit of this behavior. And now if I draw it more smoothly, it might look something like this. And I want to point out that the phase diagrams, so this is to a question that was asked, could you do it over an x-axis? You're always going to do a phase diagram over the axis of the dependent variable. So in this case, you would not do a phase diagram over x because it's the independent variable. But if x was your dependent variable, then you would do it over an x-axis, but always over the dependent variable axis. Okay, so we've drawn one typical solution. Let's draw another. And when I say typical solution, I essentially mean a solution in each interval. So we've done the middle interval. Now let's do the interval above for all y greater than -1. And you can imagine it might look something kind of like that. And then correspondingly, down here for the bottom interval, it might look something like that. These are what are called typical solutions. Now, I brought this up in terms of equilibria or equilibrium solutions. You can classify each equilibrium solution according to what happens with the typical solutions around it, or so you can either look at the typical solutions that are above and below it. You can actually just look at the phase diagram and decide right away. And there's going to be three cases. It's nice to see the slope field because to me at least, it makes more geometric sense why we would classify the equilibria this way. But the phase diagram gives you all the information you need in this regard. Now, before going on, a good question would be, oh, are these the only typical solutions? Like, do you have just one per interval? We typically just draw one per interval because any other one in that interval is just going to be a shift. If I were to draw another one, which I'll do in, let's say, orange, if I were to draw another typical solution, it would look, let's thicken it up a bit. It would look like this. And again, I'm drawing it by hand, so it's not perfect, but it should just look like a shift of this, this purple solution here to this orange one. It really is a shift. And why is that true? Well, think about the slope fields, or think about the slope lines. They are just shifted over to the right and left, but they are exactly the same. So it's like you copy paste the slope lines. So of course you're going to be copy pasting the solution curves as you move to the left and right. So you can draw more than one within a given interval, but you don't really need to because it's just going to be a repetition of the same one. So in general, typical solution is just one per interval. And now looking at what happens with these typical solutions, think about it this way. Suppose for a second that you are on the equilibrium solution. That is, let's say you are right here. So imagine you're at this at this red point here. If you're at that red point, let's say if nothing disturbs you and you just stay on that line, you're going to keep going to the right forever and just stay at the exact same height. But let's say you are disturbed a bit, like not in the like emotional sense, but like the physical sense that you're pushed off the equilibrium solution, either up or down, doesn't matter. But if, let's say, there's just a little push, a little disturbance that pushes you, let's say for the sake of our conversation here, let's say it pushes you up. So you're knocked off of this and you go a little bit up. What do you think is going to happen? So here's a way to kind of tie your intuition. So will you just type in chat what you think is going to happen if you get knocked up? Well, that sounded crazy. If you get pushed up off of the line, what's going to happen to that point then, or the solution as you move to the right? So say something like a little force kind of pushes this point and it gets pushed up off of the equilibrium line. What's then going to happen as you continue to graph the solution from there? So for example, what I mean, maybe it's not clear what I'm saying here. If there's nothing pushing this red point up or down, you're just going to continue right along this curve and nothing's going to change. But if it gets pushed up, what's going to happen to it? Just in a general sense. What do you think? Let's get some people weighing in so I can see whether you're following or not. Okay, so I'm getting some people chiming in. That's good. Thank you for those who have put something in chat. And indeed, yes, there's various ways that you guys are phrasing it, which is good, and there's various ways to think about it. If you push this point off of the equilibrium line, and let's say it gets pushed up to here, it should follow along after that, along this purple curve here, or maybe if it wasn't quite on the purple curve, somewhere else like this, it'll get pushed to infinity. It'll continually get pushed upward and so on. The important thing is that it gets pushed away from the equilibrium line. So once you've pushed it off of the equilibrium line, this thing right here, it's going to keep going up. And it's namely going to go away from this line. It's never going to come back to it. It will not go up and then like come back down. Once it moves away from the equilibrium line, it goes away from that line forever. So too, if you push this down, if you were to push the point, let's say it really got pushed down to here, it'll do something like this, and it'll get pushed away from this line. What that means is, in some intuitive sense, hopefully this gives you an intuitive idea what's going on, but this is what we call an unstable equilibria or equilibrium. The reason it's unstable is because if you just get pushed a little bit off of it, you essentially are never going to return back to it. So this is what we call, unstable. If you stay exactly on that line, you're fine. You're going to always be on that line forever. But if you get pushed off of it a little bit, you're gone forever. Compare that to the other case, where if you look at the lower equilibrium solution, let's say down here, if you move a little bit off of that equilibrium, let's say you get pushed up a little bit, then to answer someone's question, you would follow a typical solution. So there might be a typical solution that started over here and what have you. which I won't draw just so I have that room open. But you would follow along a shift of the typical solution, and that would bring you back closer to the equilibria. You would never actually reach it, but it would bring you back to it. So you can sort of think of like this case where you're pulling points in towards the equilibrium. And it happens both when you're above and when you're below, that you get pulled back in towards the equilibrium. In that case, we call it stable. If all you do, if you get knocked off of the equilibrium solution, you get pulled back into it. So it's stable. It can sort of handle a little bit of disturbance. Where in the case of being unstable, it can't handle the disturbance in some intuitive sense. You get pushed off, then you're not going to return. There's one other case, or kind of two cases of the same thing that could happen. Can you guys, maybe you can guess, we have unstable, stable. Is there, and actually someone just asked it, could you have something else? Or, well, I basically said you could. Can you imagine what else could happen? So you have unstable where you're pushing away on both sides. You have stable where you're pulling in on both sides. What else could happen? Go ahead, take a guess in chat if you can think of something. What might happen besides what we've drawn here? Okay, for those of you weighing in chat, I appreciate it. So there's a couple responses I had. Let's kind of think through them. Now, you could imagine doing various things here intuitively. You can imagine, oh, well, if I get pushed off above, I get moved away, like in the case of the unstable one. If I get pushed off below, then I move away, and so on. You could also imagine that, well, what if it's different? What if I get pushed above and then I move away, and I get pushed below and I get kind of moved back in or attracted back in? So you can have what's called semi-stable, where it's a mix of the two. I'll actually, yeah, let's just move this up. Oh. And maybe I'll put down here. So we have three cases. We have stable, which looks, so let me set this up. So we've got stable, unstable, and then what I'm calling semi-stable. The stable, as we saw, pulls in from both sides. So it's decreasing from above and increasing from below. Unstable pushes away from both sides, so it's increasing above and it's decreasing below. Semi-stable would be a case where it either increases above and below or it decreases above and below. So on one side, it's attracting solutions back towards it. On another side, it's repelling them away. Now, this is sometimes called unstable as well, but the most formal way I've seen it and the way I think of it, because it makes intuitive sense, is semi-stable. That it's stable on one side, but unstable on the other side. Okay, now let's look at an example where we can decide whether it's semi-stable, stable, or not thinking about a graph. So let's look at a new example. Let's say we have the following function, dy dx is equal to, let me think for a second. Okay, let's do, how about cosine of y? Yeah, that'll be a good one. Okay, now if we have cosine of y, one thing that we can do is we can make a graph where we graph dy dx versus cosine versus y, versus the dependent variable. So notice there's a little bit difference between what will be the slope fields, which are x versus y, the independent variable versus the dependent variable. So that's how you'd graph a slope field, how you'd graph a solution curve. But what I'm going to show here is something different. I'm going to show a set of axes where now the dependent variable is going to be on the horizontal axis, and the vertical axis is going to be the slope, dy dx. Now, why would you do this? Where I've seen this done is really only in this case, as far as this class. I don't think you need to, or maybe it even really helps doing it in other cases. So this is really a graph you would do when you're looking at autonomous differential equations. Or maybe phase diagrams. Now, if we graph dy dx versus y, we're essentially graphing the function cosine of y is equal to dy dx. Let me put that in yellow. So if we graph cosine of y, where now y is on the horizontal axis, cosine will simply look like this. Roughly, again, I'm drawing it by hand, so forgive the imperfection. Now, what's interesting about this is it essentially gives us the phase diagram immediately once you're comfortable with these ideas. One thing to note is that it shows us right away where we are zero for the slope field. That is, we know that at this point, and so on, we're equal to 0. And then using the color that I did in the last example, we know that here we're positive, here we're positive, here we're positive, and notice it does oscillate. And then in these areas we're negative. Now from that, we can right away get the phase diagram and what the phase diagram looks like. And if it's a little confusing keeping track of all the different graphs with the different axes, I totally understand that. I'm sure you're not alone. But let's graph the phase diagram. Actually, let's put the phase diagram between these two. So here, use your intuition that you've developed, as far as you can remember, to imagine that the phase diagram is just a smushed slope field. It's just crushed along the x-axis. So it's like the slope field, but you just have the y-axis part, and you're tracking essential information. Now there's going to be a switch going from this to this, because notice that the y-axis is horizontal here and it's vertical here. But if you want, I'll also, or if it helps, I'll also do the exact same phase diagram down here in what might be in some sense more intuitive. So I'm going to look at these points where there's an equilibrium, and I'm going to graph those. If I just directly translate down here, I mean, that's easy enough to do. So if I have, let's say, about there, and so on. Okay, we have the equilibria, and those, just for reference, are going to happen where? They're going to happen at pi over 2, 3 pi over 2, and so on. Negative pi over 2, negative 3 pi over 2. Notice that I'll then do those exact same points or values down here. And I got those just by figuring out where cosine is equal to 0. And then I'm just going to rotate this. I'm going to take this thing, maybe let's do it a little darker. Take this thing and I'm going to rotate it like this. And as I rotate, what I'll get is exactly this. And that looks like here, here, here. And those are the same values, 3 pi over 2, pi over 2, negative pi over 2, so on. Now I set this up to hopefully make it easy to see quickly that if we translate down here, we have a positive value. So that means we've got positive there. We've got positive here. I mean, there's more oscillation afterwards, but immediately after it is positive. So let's draw that really clearly. It's positive here. And we also get that there are these negative parts or negative intervals like so and so. And that, of course, corresponds exactly to this. So looking at the graph like this, we can quickly draw the phase diagram. Now, if we look at these different equilibria, like y is equal to 3 pi over 2, that's one equilibrium, then each of them are either considered stable or unstable. So we have equilibria. One is y is equal to 3 pi over 2. And now my question for you guys is this stable or unstable? You can just say in chat whether you think it's either one, gives you a chance to test your memory here, and then also for me to see if you're getting this. So are we stable or unstable specifically at this equilibrium? That would correspond to this one here. Okay, good. Thank you guys for checking in. Indeed, it is unstable because it pushes away in both directions. If we looked at this one, pi over 2, that would be stable. It pulls in from both directions. We don't have any semi-stable. There's no cases where it pulls in from one direction and pushes away. But that's essentially it. Let me say one more thing in the last minute-ish, and that is the following. You'll have a lab on logistic equations, and I just want to highlight something. We won't get that far into it, which is totally okay. It wasn't really necessary that we got deep into logistic equations, but I want to just point something out for you to think about, and don't worry about it too much. Just let it sit in your subconscious until you get to the lab. There is a population growth model. this will just take a minute. There's a population growth model where your change in population, let's say capital P, with respect to time, is dependent on how much population there is. So imagine you have just a couple people, you're only going to have a couple children. If you have a lot of people, there's going to be more children being born in general. This R is just some rate. Maybe the birth rate is 1%. Maybe that seems low, but whatever it is, it's every year you add X percent to the or add R percent to the population. There's a difference between that, which if you graph it, and I'm really just going to show the graphs of this, and that's going to be it. If you graph this thing, what you'll get if you graph solutions to it, you'll get things kind of like this, where they grow and grow and they never stop. That's not realistic because eventually you're going to hit what we think of as a carrying capacity for an environment. You won't have enough food, or something else will happen. You won't have enough space. So you won't always be able to grow without bound. And that's why there's something called a logistic equation model, where notice here, there are two equilibria. One when P is 0, and then one when P is equal to K here. So you'll have essentially behavior like this. And the reason being, and this is the last thing I'll say, is you have an equilibrium here and here, whereas in the case you only have one equilibrium there. And you'll see more with logistic equations later. I just wanted to introduce that idea to you. Okay, with that, you guys have a good day. We'll see you or talk to you on Friday. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.